Okay, so now the next thing I want to do is I want to talk about how you figure out the electron configurations of molecules of two identical atoms that are bound together and where those two atoms are found in the second period. And so one thing we sort of have to do is familiarize ourselves with a diagram that probably will be on your test or on your homework assignments that can help you figure out what the electron configuration of these molecules are. And so we have a picture of the diagram here. So what I want you to notice is several things. One thing, there's sort of two parts to the diagram. There's a part here on the left, and then there's a part here on the right. They are similar, but they are a little different from one another, and so I'll tell you how they're different from one another later. Also, I want you to notice is that here what we have is we have written out all the atomic orbitals of the second energy level and the molecular orbitals that form from them in the second energy level on an energy diagram. And so we have increasing energy going up here. So now let's just kind of focus in on the left side here of this diagram and see what it may be telling us. So one thing I want you to notice is there's sort of on the left side two portions. There's this portion down here which is in light blue, and then we have a portion up here which is, I guess, sort of a light pink color. So what you can see is the light blue region. This is a description of how you can take two s orbitals in the second energy level of two different atoms and form two molecular orbitals. One will be a 2s sigma orbital, and the other will be a 2s star sigma orbital. And so the one that is sigma 2s here is a bonding orbital, and this one is an antibonding orbital. Now, above that and higher in energy is a description how you can take 3 p orbitals on each atom for a total of 6 p orbitals here, and then how you can mix them together to form 6 molecular orbitals. And so here there will be a pair of molecular orbitals relatively low in energy called the pi 2p, and then we have here another one that's higher in energy, that is sigma 2b, and then we have a antibonding pi 2p and the sigma antibonding 2p orbital. And so those are the 6 molecular orbitals that are formed from the atomic p orbitals. Now this left diagram here, it basically applies for when you're trying to figure out electron configurations for molecules or molecular ions where both atoms are either boron, carbon, or nitrogen. Now, let's say you don't have that. Let's say instead you're trying to find an electron configuration of a molecule of a molecular ion that is made of 2 atoms of oxygen, 2 atoms of fluorine, 2 atoms of neon. You will use a slightly different diagram. And so what you'll see is that the lower portion of the diagram here is the same as that used for boron, carbon, and nitrogen, but the upper portion is a little bit different in that here we have some energies of the molecular orbitals formed that have changed slightly. And we'll talk a little bit more about this later. So now what I want to do is talk about how do you figure out the order of energy for the molecular orbitals formed for, say, when you have 2 boron atoms combining or carbon atoms or nitrogen atoms binding. And so unfortunately, what you're going to have to do is memorize the order in terms of energy of the molecular orbitals that are filled. And so what you can see here in this lower portion of this diagram here, we have some orbitals, but then as we go up, we have more molecular orbitals that are filled. And again, we're not going to so much pay attention to the atomic orbitals that are used to derive the molecular orbitals. We're just going to look at the molecular orbitals in particular. So the way you might remember this, and this is from Dr. Woodrum. Dr. Woodrum suggests is that you sort of think about this arrangement of molecular orbitals in terms of energy as a Christmas tree. So I'm going to draw a Christmas tree here. So here's the base of the Christmas tree, and then it goes out, and then it goes in, and then it goes out here, goes in again, like this, and then it goes out, in, and you form the base again. So wherever this is narrow, that is where the single sigma molecular orbitals are found. But then where the tree is a little bit wider, that is where you find 2 of the pi orbitals. And so we'll practice this again in a minute. So as I kind of pointed out to you earlier, if instead you're trying to figure out the electron configuration of a molecule or a molecular ion of oxygen, fluorine, and neon, the order of the molecular orbitals in terms of energy is different. And so I'm showing you with a circle where that difference is. And so you have to know that difference. And so this difference occurs is because you have something called sp orbital mixing that is occurring in boron, carbon, and nitrogen molecules that is not occurring in oxygen, fluorine, and neon molecules. And I'm not going to talk about that anymore, but if you're curious to learn more about that, what you can do is you can click on this link to an online textbook called OpenStax, and it'll tell you a little bit more about sp mixing. But what you really have to know is what the order of the orbitals are for oxygen, fluorine, and neon molecules. And so here's what I thought of. So here we don't have so much a live Christmas tree. Instead, we have a dead Christmas tree. Yep, the Christmas tree died because you forgot to water the Christmas tree, and it defoliated and it died. Yeah, so you have to be a little bit more careful next Christmas and make sure that the tree is watered. So anyway, just recall that when you're dealing with oxygen, fluorine, neon, you're dealing with a dead Christmas tree. And so the areas where you have the narrowness of the tree, which includes the stem of the tree and the base of the tree, is where you have sigma orbitals. And then here, the areas where it's wider apart, then you have the pi orbitals. Okay, so now let's go ahead and see if I can draw trees and recall the order of the molecular orbitals in terms of energy. So the first thing I'm going to do is I'm going to draw a diagram that represents the order of molecular orbitals for molecules that are formed from 2 boron atoms, 2 carbon atoms, or 2 nitrogen atoms. And so this is Dr. Woodrum's live Christmas tree. So I'm going to draw the live Christmas tree like this. So it looks like this. Gotta have sound effects here. So live Christmas tree, doing well. Okay, and then we're going to write out the order of orbitals in a minute. But on the other hand, if you have the other elements of the second period with more protons, that would be oxygen, fluorine, and neon, you don't have a live Christmas tree. Nope, you have the dead Christmas tree, the one you forgot to water and it defoliated. Yeah, it's your fault. Okay, so now let's go ahead and figure out the order of the molecular orbitals. And so if you're dealing with boron, carbon, and nitrogen atoms, and so you will hopefully remember is that these Christmas trees represent molecular orbitals in the second energy level. And so what I'm going to do is I'm going to draw lines for these orbitals and then I'm going to name them. And so at the base of the tree, you start out with the sigma 2s orbital, and then the next one up is the sigma star 2s orbital. Now we go into the base of the tree. And so these are the molecular orbitals that form from the p atomic orbitals. And so you first hit the base of the tree. So that tells you that in terms of energy, the next ones are not a sigma orbital, but a pair of pi orbitals. So we have to draw 2 pi orbitals like this. They're pi, like this. And so this is going to be a 2py orbital, and this is going to be a 2pz orbital. And so what is the next orbital up? Well, now we have to deal with a sigma orbital because we're now in sort of the narrow part of the tree. So this is a sigma, and then this is 2px. And then what is next up in terms of energy? Now we're getting into the antibonding orbitals. And so next up are the pi 2p orbitals. So we have pi 2py, that's an antibonding orbital. And then we have pi 2pz, this is an antibonding orbital. And then the final orbital at the top of the tree is going to be a sigma orbital because this is where the tree is narrowest. So it's going to be sigma 2px, and this is an antibody orbital. And so this is a good description of the order in which the orbitals are filled if you're dealing with either boron, carbon, or nitrogen molecules. Now, if you're dealing with oxygen, fluorine, and neon molecules, you have to deal with the dead tree, yeah, the one that you killed. And so what you have to do is you have to remember the order of orbitals here. And so it's very similar at first. And so you start out the lowest with sigma 2s, and then you have sigma 2s star for an antibonding orbital. And then now what you go on, you're going into now the p orbitals that are formed. But the p orbital, the first p orbital is going to be one that's not a pi orbital because we're still in the narrow part of the tree. So this is going to be a sigma 2px orbital. Now we're getting into the wide part of the tree. And so now we're in the pi orbitals. So this is going to be pi 2py. This is pi 2pz. Now the next one's up. You're still in the wide part of the tree. So this is pi 2py. This is going to be an antibody orbital. So we have an asterisk here. And then we have pi 2pz. This is an antibody orbital. So we have an asterisk here. And then finally we end up with the top of the tree, which is going to be sigma 2px star. So hopefully you can remember that order of orbitals in terms of their energy. So moving on. So now here is sort of a description of some of the rules that you use to figure out the electron configuration of these molecules using these molecular orbital energy diagrams. The first rule is that the number of molecular orbitals formed is always equal to the number of atomic orbitals combined. I think you saw that in the previous slides. The next rule, which is pretty important, is that the filling of molecular orbitals always proceeds from lower to higher energies. You'll see an example of that in a second. The third rule which you'll apply is that each molecular orbital can accommodate up to 2 electrons. So it's very similar to atomic orbitals. The fourth rule is that if you have 2 orbitals of the same energy, in other words, they're degenerate orbitals, then we use Hund's rule to add electrons to those orbitals. So we put 1 electron in each of the equal energy orbitals before we put 2 in one. The next rule is that the number of electrons in the molecular orbital is equal to the sum of the electrons on the bonding atoms. And then one thing you'll just have to sort of keep in mind as you're doing these electron configurations, if you're using these diagrams that describes the second energy molecular orbitals, don't forget that you have electrons that you put into the molecular orbitals that were formed from the first energy level. So let's go ahead and do some examples of this. And so here's a good example. This is something you might see on your test, for example, in that you will be asked to figure out what the electron configuration and the bond order of the B2 molecule is. And then what we're going to have to do is we're going to have to figure out if this B2 molecule is either paramagnetic or diamagnetic. So here is the formula of the molecule. It's probably something you're not quite used to. This is B2, and so here what we have is a situation where you have 1 boron atom stuck to another boron atom. Now normally you will not see 2 boron atoms stuck together, but there are certain circumstances where you might get this molecule. And so we're pretending that we're in these circumstances, and we have to figure out what the electron configuration of the B2 molecule is. So how do we do that? So we're going to use this diagram here, which shows us the relative energy of the second energy level molecular orbitals. We're going to use this diagram to help us. Now, one thing I want you to notice is that we're going to use this diagram, we're going to fill this diagram with electrons, but again, it's only showing us the molecular orbitals that are found in the second energy level and does not include molecular orbitals that are found in the first energy level. So what we have to do is we can only add electrons into this diagram that are found in the second energy level of boron. So let's talk a little bit about that. So you can see the location of boron here in the periodic table. Boron naturally has 5 electrons, right? And so what you might remember is that 2 electrons are in 1s, and then you have 3 more electrons, 2 are in 2s, and 1 is in 2p, and then there are, of course, these other 2p orbitals here. Now, here, just again to note that this diagram here only applies for electrons in the second energy level. So, although boron has a total of 5 electrons, when we're trying to figure out the electron configuration, what we're going to do is we're just going to focus on the highest energy level electrons, which are the valence electrons of boron. So although boron has 5 electrons total, it has a total of 3 valence electrons. And so you would sort of know that by looking at the periodic table. And what you'll notice is that boron is in group 13 here, which you can sort of see here. So group 13. So if it's in group 13, it'll have 3 valence electrons. So again, we're going to use this diagram to help us figure out the electron configuration of the B2 molecule. So one B atom has 3 electrons, but we have another B atom which has 3 electrons. So we have a total of 6 electrons. Okay, so now what we're going to do is we're going to use this diagram of valence molecular orbitals to figure out the electron configuration. So at this point, we can just sort of forget here these spaces for atomic orbitals. Those spaces there were just used to tell us how the molecular orbitals were formed, so we don't really have to worry about the slots or the spaces for the atomic orbitals. What we do have to worry about are the slots or the spaces for the molecular orbitals. Okay, so again, we have 6 valence electrons in B2. So the first 2 electrons will go into the lowest energy molecular orbital available, which is the sigma 2s orbital here. So we're going to put 2 electrons there. And the next 2 electrons will go into the next lowest energy molecular orbital, which is sigma star 2s. They go here. And then that's 4 of the 6. And the last 2 electrons will go into the next lowest energy up. And so one goes into this pi 2p orbital. And then you can see that we have another pi 2p orbital. It is exactly the same energy as the first. So this is where Hund's rule applies, in that you have 1 electron in one of these orbitals. If you have another orbital of equal energy, we have to put 1 electron there before we pair them up. Now, that is the correct putting in of the electrons into the molecular orbitals. And now what you have to do is write out the electron configuration for the B2 molecule. So what I'm going to do is I'm going to notice here that there are 2 electrons here in sigma 2s, and so this is how I write this out. I write in parentheses sigma 2s with 2 electrons. And then I notice that there are 2 electrons in the 2s antibonding orbital here, so it's sigma star 2s with 2 electrons here. And then I notice is that we have, looks like, 2 total electrons in the 2 pi 2p orbitals. So one of the pi 2p orbitals is the one formed by the atomic p orbitals oriented on the y-axis, and one is formed from the atomic orbitals that are oriented on the z-axis. Okay, and so the way you can write this out is these are pi 2py, we have 1 electron in that, and then we have pi 2pz, and we have 1 electron in that. Now, we are not quite done with this electron configuration, because you have to remember that these are the valence electrons that we have a configuration for, but we need to write out the entire configuration of B2. And so we also have to include the core electrons that are in the core molecular orbitals. And so there's going to be a sigma 1s orbital, molecular orbital, which we talked about earlier. It has 2 electrons. And don't forget about the sigma star 1s orbital. That also has 2 electrons. And so this here, what I have here, is a good electron configuration for the B2 molecule. Now let me show you another way to write this. So you write it starting out in the same way. It's sigma 1s 2, and then sigma star 1s 2, and then sigma 2s 2, and then sigma star 2s 2. Now, what you'll see in a lot of textbooks and maybe in your Achieve homework is that they will not separately designate the 2p molecular orbitals into y and z. They just kind of mix them together. So instead of saying 1 electron in 2py and 1 electron in 2pz, what they'll say is we have in the 2p orbitals, we have 2 electrons there. And so that will be an equally good configuration. Now, can you figure out the bond order? Now, we talked about this last time. So the bond order is equal to 1/2 the number of electrons in bonding orbitals. And so to represent that, I'm going to write a capital B and then an E, minus the number of electrons in antibonding orbitals. And to represent that, I'm going to write A, B, E. So if you do that calculation, let's see what we get. So how many electrons do we have in bonding orbitals? And so here we have 2 electrons in this bonding orbital here. We know it's bonding because there's no asterisks in this symbol here. This is not here a bonding orbital. This is an antibonding orbital because this has an asterisk. But these final 2 electrons, the highest energy ones in the pi 2p, there is no asterisk there. So those are bonding electrons as well. So it looks like we have a total of 4 bonding electrons. Now, how many antibody electrons do we have? Well, the antibody electrons are the ones that are in the antibody orbitals, and so we have 2 electrons here in this antibody orbital here, which I'm circling now. So it's 2 there, and that's it. And so here, if you do this calculation, you'll find that the bond order for the B2 molecule is 1. So what does that mean? The bond order tells you the number of bonds that is going to be predicted to be bonding these 2 atoms together. So one possibility could have been that maybe boron between its atoms has 3 bonds, or maybe another possibility is that between the boron atoms there was 2 bonds, or maybe another possibility there's only 1 bond. And so when you see a bond order of 1, what that indicates that the answer is that when you have the B2 molecule form in those unusual conditions where it does, then you can expect there's only going to be 1 bond between the 2 boron atoms. And if you have 1 bond there, you would expect only 2 electrons to be found in that bond between the 2 boron atoms. Okay, the final question, is this B2 molecule, is it paramagnetic or diamagnetic? So let's remind ourselves when you have a diamagnetic atom or molecule. You have a diamagnetic atom or molecule when for all the orbitals that have electrons, you always see a pair in the orbitals. So if all orbitals have pairs of electrons, then that molecule will be diamagnetic. On the other hand, a molecule will be paramagnetic if there's at least 1 orbital that does not have a pair of electrons, but rather has a single unpaired electron. Now, it can have more than 1 than that. So if you have a molecule that has 1 or more orbitals with a single unpaired electron, that would be a paramagnetic molecule. And so I think what you can see that the highest energy molecular orbital, which is the pi2p orbital here, it has a single electron in each orbital. And so this predicts that this will be a paramagnetic molecule. Okay, let's do the next one. So now what we're going to do is we're going to try to find the electron configuration and the bond order of the fluorine molecular cation. So what this is you have 1 fluorine bound to another fluorine atom like this. I'm going to try to draw atoms here, but it's missing 1 electron than normal, so it has a positive charge. And so this is called a molecular cation. It's a molecule because you have 2 atoms bound together. It's cationic because it's missing 1 or more electrons. Here it just happens to be missing 1 electron. Okay, so what we're going to do is we're going to use this diagram on the right, which shows us the energy of the molecular orbitals that are found in the 2nd energy level. These would be the valence molecular orbitals. And so what we're going to do is we need to count the total number of electrons found in this molecule, but then only add valence electrons to the diagram. So let's just see how many total electrons we would find in the F2 molecule. Well, fluorine has 9 electrons, and there are 2 of them, right? So there would be a total of 18 electrons in the molecule, but it's missing 1 electron. It's a cation, so there are really 17 total electrons in the molecule. However, what we're going to do is we're going to use this diagram over here to figure out what the electron configuration of the molecule is. And so here, what we're going to do is we're only going to fill in valence molecular orbitals. If so, then we're only going to count valence electrons in this molecule. So fluorine here, for valence electrons, you might remember because fluorine is in column 17, it has 7 valence electrons. The other fluorine atom has 7 valence electrons. And then, so we have a total here of 14 valence electrons, but it's missing 1 extra electron, so it's a cation, so we're really dealing with 13 valence electrons. So let's go ahead and fill this diagram with 13 electrons. So first pair go here, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so this is correctly filled out. So now, can you write out what the electron configuration is for the fluorine molecular cation? So let's see, we'll start out here. We have the 2 electrons in the sigma 2s. So I'm going to write here sigma 2s, 2 electrons. And then we have 2 electrons in sigma 2s star. So sigma star 2s. Then what's the next one up? Well, fluorine is going to be a 2px orbital, so it's sigma 2px with 2 electrons. I should have put a 2 there. And then what's the next one up? And so here we have pi 2py, 2 electrons, and pi 2pz, 2 electrons. And then finally what we have, I'm going to just keep this going here, we have 2 electrons in the antibody pi orbital of the y, so it's 2py, we've got 2 electrons there. And then we have 1 electron in the antibody orbital of the 2pz, so I'm just going to indicate there's 1 there. Now again, this electron configuration notation is not complete because we don't want to forget about the electrons that went into the core molecular orbitals, so don't forget to write in sigma 1s, 2, and sigma star 1s, 2 like this. So this should be a good electron configuration for the fluorine molecular cation. So I'm going to write this in a different way in the shortened form, which you might see on your Achieve homework. So this way I just wrote is acceptable, but you can also write it like this. You can sigma 1s, 2, like we did before, sigma star 1s, 2, no difference there. And then sigma 2s, 2, sigma star 2s, 2. And then you have sigma 2p. We can leave out the x here and put a 2 there. Now notice we have 2 electrons in the pi 2py, and we have 2 electrons in the pi 2pz. But what we're going to do is we're just going to lump those all together and say we have 4 electrons in the pi 2p bonding orbitals. So to do that, we have write pi 2p. This is bonding, so we don't have an asterisk, and so we put a 4 here. And then we do something similar up here. We have 2 electrons into the antibonding pi 2py orbital, and we have 1 electron in the antibonding pi 2pz orbital. Let's just say there are 3 electrons in the antibonding pi 2p orbital. So you can write pi 2p antibonding like this, 3, and so that should be correct. Okay, now let's go ahead and figure out the bond order. So the bond order is going to be 1/2 the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals, and so it's going to be 1/2 2 electrons in this bonding orbital here, 2 electrons in this bonding orbital, and we have 4 electrons here in this bonding orbital, so it looks like we have 2, 4, 8 bonding electrons. And now how many antibonding electrons do we have? Well, we have antibonding electrons in this sigma 2s star orbital, so 2 here. 3 more in this pi antibonding orbital as 2py and 2pz, so there are 3 electrons here. So it looks like we have a total of 5 antibonding electrons, so we have 5 here. So it's going to be 1/2 8 minus 5 is 3. And so here what you can see is that the bond order is 3/2 for this molecular cation. So what does that mean? Well, what that means is if you have 2 fluorine atoms stuck together, if you have a bond order that's 3/2, that's a half more than 1, right? So you have 1 bond at least with 2 electrons. And again, this is a half more than 1. So maybe you can imagine that there's an additional electron that is a part of this bond. So maybe when this molecular cation forms, you have not 2 electrons between the fluorine atoms and not 4 electrons between the fluorine atoms, but instead you have 3 electrons between the fluorine atoms. Now the last question we're going to ask is this molecular cation, is it a paramagnetic or diamagnetic? And so I think what you can see is that we have 1 orbital here that is filled with just 1 electron. If that is the case, that renders the molecule paramagnetic. Okay, so let's move on. Okay, so there's one more thing I want to point out. So remember at the beginning when we were talking about molecular orbital theory, we were trying to come up with a new theory in part to explain some strange behavior of the oxygen molecule. So if you are able to cool the oxygen molecule to be in the form of a liquid, then if you send that liquid between 2 posts of a magnet, it will get stuck between those 2 posts, as you can sort of see in this picture here. And so what that indicates is that the oxygen molecule is a paramagnetic molecule. And the reason why it's paramagnetic is because it's attracted to magnetic fields, and so it can get stuck between the poles of a magnet. Now, if you look at the regular Lewis structure here of the oxygen molecule, what you can see, it looks like all the electrons here in the Lewis structure, which is correctly drawn, are in pairs. So the way we drew this Lewis structure, we're indicating that all electrons in the molecule are in pairs. And so we would predict, based on looking at this Lewis structure here, that the molecule, the oxygen molecule, would be diamagnetic. But you can see it's not. You can see here it is paramagnetic. So how does molecular orbital theory help us understand that oxygen is truly paramagnetic? And so we can see that here. And so what we've done here is we have written out the electron configurations of these second period elements. Let's focus in on oxygen here. And what you can see in its electron configuration, all of its electrons are paired except for the highest energy level electrons. And so we have one electron in one of the 2p y orbitals and another electron in the 2p z orbital. These are antibonding orbitals. And so it's these unpaired electrons that explains why oxygen is paramagnetic. So normally you might draw a Lewis structure for oxygen like this. And this sort of implies that all electrons in molecular oxygen are paired. But maybe a better way to draw it is like this. So we have one oxygen atom here, we have one oxygen atom here, we have a single bond here for now, pair of electrons here, pair of electrons here like we had before, pair of electrons here, pair of electrons here that we had before. Now what I'm going to do is I'm going to take the bond that normally would be here and break it into individual electrons, put one electron here on this atom, one electron here on this atom. And so here, this may be a more accurate representation of oxygen in a Lewis structure. So obviously this isn't the best Lewis structure, but this structure reminds us that the oxygen molecule has two orbitals with unpaired electrons, which causes it to be paramagnetic. So thank you for listening to that, and we'll see you next time.